Hey, today we're going to look at a powerful technique for computing limits known as L'Hopital's rule. And here's what it says. It says, suppose you have two differentiable functions, f and g, and you're trying to compute the limit as x approaches a of f of x over g of x. Well, suppose if you directly substituted x equals a into both of those functions, you would get something of the form 0 over 0, or positive or negative infinity over infinity. Then L'Hopital's rule says that the limit as x approaches a of f of x over g of x is precisely equal to the limit as x approaches a of f prime of x over g prime of x, the derivative of f divided by the derivative of g. And the beauty here is that this second limit, the limit as x approaches a of f prime of x over g prime of x, might be easier to compute than the original limit. So that's the idea. And it's worth mentioning some terminology. We call 0 over 0 and infinity over infinity indeterminate forms. What is 0 over 0? Well, 0 over anything is 0. Anything divided by 0 should be infinity. Anything divided by itself should be 1. 0 over 0 could be anything. And similarly for infinity over infinity. You can't determine what these are without doing some work. And it's also worth mentioning before we proceed that although we've stated it in terms of x approaching some number a, L'Hopital's rule also applies for limits as x approaches infinity or negative infinity, and it also applies to one-sided limits. And before we're done today, we'll look at a proof of at least one of the cases of L'Hopital's rule. But before we do that, let's apply it to some examples. And the reason I wanted to start with this particular example is that you've already seen it. I believe it was the first day of class we looked at this limit. And what we did was we simply computed the values of e to the 3x minus 1 over x for values of x getting successively closer to 0, and then made a guess at what the limit was. And then we also looked at a graph of the function, and that confirmed our guess that the limit as x approaches 0 of this function is actually equal to 3. But now we can actually compute it instead of guessing or graphing, and use L'Hopital's rule. This is of the form 0 over 0, and so L'Hopital's rule says that this limit is equal to the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. And by the chain rule, the derivative of the numerator is 3e to the 3x, and the derivative of the denominator is 1. And that's a very easy limit to compute. You simply plug in x equals 0, and you get 3. And that confirms our guess from earlier in the semester, but now we didn't have to guess. We got to actually do a computation and come up with a definitive answer that the limit is equal to 3. Let's do another one. The limit as x approaches infinity of 6x squared plus 3x plus 4 over 5x squared plus 7x plus 3. We've already looked at limits like this in this class, and we did it by using algebra and the limit laws. We divided numerator and denominator by x squared, and then applied the limit laws and came up with some answer. But in this case, you could notice that as x approaches infinity, the numerator is approaching infinity, and the denominator is approaching infinity, and so this has the form infinity over infinity, and so we can use L'Hopital's rule. And by L'Hopital's rule, this limit is equal to the limit of the derivative of the numerator divided by the derivative of the denominator, and the derivative of the numerator is 12x plus 3, and the derivative of the denominator 10x plus 7. And how do you take this limit? Well, once again, we could use algebra and the limit laws, but once again, it's still of the form infinity over infinity. And so we can use L'Hopital's rule to take this limit as well. And by L'Hopital's rule, this limit is the limit as x approaches infinity of the derivative of the numerator divided by the derivative of the denominator. And since the derivative of the numerator is 12 and the derivative of the denominator is 10, this just gives us 6/5. Okay, your turn. Try all 5 of these. Pause the video. When you're all set, start it back up, and we'll go through them together. For the first one, sine of 0 is 0, so this is of the form 0 over 0, so we can use L'Hopital's rule. And this limit is equal to the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator, which is the limit as x approaches 0 of the cosine of x divided by 1. That's a very easy limit. You simply plug in x equals 0, and you get that the limit is equal to 1. For the second one, plugging in x equals 2, we have something of the form 0 over 0, so we can use L'Hopital's rule, which gives us the limit as x approaches 2 of the derivative of the numerator, 4x cubed, divided by the derivative of the denominator, which is 1. And that's a nice easy limit. You simply plug in x equals 2, and you get 4 times 8, which is 32. The third one is less obvious. You need something of the form infinity over infinity or 0 over 0. It's not written that way, but you simply have to remember that e to the negative x is the same thing as 1 over e to the x. And so just algebraically, this is the limit as x approaches infinity of x squared over e to the x. And that is of the form infinity over infinity, and so we can apply L'Hopital's rule. By L'Hopital's rule, this limit's equal to the limit of the derivative of the numerator divided by the derivative of the denominator, and the derivative of the numerator is 2x, and the derivative of the denominator is e to the x, and so we get this limit right here. This is also of the form infinity over infinity, and so we can apply L'Hopital's rule again. And that yields the limit as x approaches infinity of 2 over e to the x. This is not of the form infinity over infinity. We have 2 over infinity, or something of the form 2 over infinity. And if the denominator is getting large without bound and the numerator is staying 2, these numbers are getting closer and closer to 0, this limit simply equal to 0. For this fourth one, if you plug in x equals 1, well, the natural log of 1 is 0, and so we have something of the form 0 over 0. That lets us apply L'Hopital's rule, and we get that the limit is equal to the limit as x approaches 1 of the derivative of the numerator, which is 1 over x, divided by the derivative of the denominator, which is 1. That's a very easy limit to compute. You plug in x equals 1, and you get that the limit is equal to 1. And for the last one, if you try to apply L'Hopital's rule, you get the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator, which is 1 over 1, which is just 1, which is not equal to the limit. And so it would be all wrong. Why? Because I tried to trick you here. This is not of the form infinity over infinity, or of the form 0 over 0, and so you can't use L'Hopital's rule here. This is just a straightforward limit. It's a rational expression, perfectly well defined at x equals 0. You plug in x equals 0, and you get that the limit is equal to 1/2. There have been a few sort of morals of the story along the way here that I haven't pointed out explicitly, so I'll stop and say them right now, and we just saw one of them. You can only use L'Hopital's rule when you can use L'Hopital's rule. In other words, make sure that you really have something of the form 0 over 0 or infinity over infinity before you apply L'Hopital's rule. Otherwise, you'll simply get the wrong answer. Another moral of the story that we saw along the way that I didn't explicitly call out and maybe should have, is that sometimes you have to apply L'Hopital's rule more than once. You start with something of the form, say, infinity over infinity. You apply L'Hopital's rule, you come up with a new limit. It might still be of the form infinity over infinity, in which case you apply L'Hopital's rule again. That can go on another time and another time, etc., until you have some limit that you can actually compute. And then the third thing that I want to say very explicitly is L'Hopital's rule deals with the limit as x approaches something or other of some function divided by some other function, and says that the limit is equal to the limit of the derivative of the top function divided by the derivative of the bottom function. There's no quotient rule kind of thing going on here. We're not taking the derivative of the entire function f of x over g of x, which would require the quotient rule. We're simply looking at a way to find a limit by using the limit of the derivative of the numerator divided by the derivative of the denominator. So I'll say it again. Don't use the quotient rule. We're not trying to find the derivative of the entire function. Okay, I'd like to give you what I'm going to call a pseudo-proof of L'Hopital's rule. We'll only consider the case where the limit as x approaches a of f of x over g of x is of the form 0 over 0. And I'm going to make the extra stipulation that the derivatives of f and g are both continuous at the point x equals a. And if that little technicality bothers you, just consider that, when does that happen? Well, every function that we have ever looked at so far. So you would have to go out of your way to come up with some function where the derivative is not continuous at the point x equals a. Okay, let's start with the limit as x approaches a of f prime of x over g prime of x. Our goal will be to show that this is equal to the limit as x approaches a of f of x over g of x. And since f prime and g prime are both continuous at x equals a, the limit as x approaches a of f prime of x is just f prime of a, and the limit as x approaches a of g prime of x is just g prime of a. And we had a couple of different definitions for the derivative of a function at a point. If we go back to our original one, then we can rewrite this expression as the limit as x approaches a of f of x minus f of a over x minus a, that's just f prime of a, over the limit as x approaches a of g of x minus g of a all over x minus a, that's just g prime of a. And then applying the limit laws, the quotient of the limits is the limit of the quotients, and you can do a little algebra and the x minus a's cancel, and you come out with the limit as x approaches a of f of x minus f of a all over g of x minus g of a. And now we're nearly done. Since we started with the hypothesis that the limit as x approaches a of f of x over g of x is of the form 0 over 0, that's telling us that f of a is 0 and g of a is 0. Which leaves us with the limit as x approaches a of f of x over g of x, which is just what we were shooting for. Okay, that was L'Hopital's rule in its most straightforward form. There are some slightly trickier problems that we also have to address that will be in the following video, but for now, you're in good shape to do almost all of the homework assignment on L'Hopital's rule. So have some fun with that, and I look forward to seeing you in class.